All right, so hello everyone. Welcome back to the sixth section. And last time in the section 5, what we've been doing is creating that bar element using the central difference method. And we say that the bar element can automatically satisfy the large deformation, can capture these large deformation and geometrical nonlinearity. So this time, what we hope to do is to push these bar elements and combine them to make a assembly. So, right, if you go back to the section 5 and when we do the verification, all of these examples that we've done last time, they just have a single bar, right? That's what we have last time. So this time we're going to cover a little bit more theory part behind these direct stiffness assembly method. That is typically behind all the finite element code that we're going to be using for simulating the deformation of a deformable body or active structure systems. So the question we want to ask is actually this title here. So what if I have two springs? What should I do? Right. So for instance, in a case where I have two springs, it would be just look like these elastic strings, right? We have three nodes, right? One, two, and three. And each of the nodes, they will have some sort of reaction forces in them. And we really want to learn what are those forces, right? So for instance, on my right hand, that there's going to be a force I'm applying. With the deformation, I'm going to be curious to learn how many forces my hand must give to the spring so that I can maintain the equilibrium. If I let go, the spring, of course, springs back. So with the deformation, with the geometry, we are able to solve for the responses from these springs. Um, the forces coming out from the spring, but we need to figure out a way of converting those forces from the spring into the forces at a node, and that's usually what we call force assembly or matrix stiffness matrix assembly or the force vector global force vector assembly. So this is represented here in this figure, kind of a very similar case like what I just showed you with the physical model. So we're looking at IJK 3 node. We're going to try to move the J's node a little bit upward with zero point 0.01 displacement, and I want to figure out what kind of forces my entire system is taking and what kind of forces I need to apply to that J's node so that I can maintain the equilibrium of the full system. So from what we have last time, we can easily design, we can easily input these nodal coordinates, set up the bars. Let's say we assume that still the stiffness constant would be just one for everything to make our life simple. And using that bar element we developed last time, we can get these local bar force vector out easily, right? So each of them would be 6 by 1. And each of the bar force is represented here. It's going to be 3 component per node. And each of the nodal components is going to be in the X, Y, Z direction. So here, B11 is the forces in the X direction. 1, 2, it's perpendicular. It's coming out of the screen. In your face's direction, and B12, that is the Y direction, and then B13, so that's the Z direction component of this force. So of course, at the end of the day, you would expect that for any sort of a bar. If you do the vector sum of all the 3 components, your sum of forces should eventually give you a result that is um, aligned with the bar's axle. So that's what we need for these bars to truss element. And that's something we will need to make sure that it's satisfied. But anyway, we are able to calculate this using the bar class we created and verified last time. So this is directly using the central difference bar elements. That's the solve local force function we learned in the section 5. And we can directly use that to get two 6 by 1 vector. And they're giving us these forces that's acting on each of those bars. But if we go back to the full system, right, we have three node, right? Just the three screws, they are representing the three node. We need in the global force, we need something that's 9 by 1 because I have three node. In each of the node, I have a force in the XYZ direction. So let me draw that out. So in this, I would need to have anyway, three component, right? So that's the nine forces subcomponent for the three node that we're going to be looking at. So essentially, we need to assemble this into this global force vector. And this is actually more straightforward than you might think. So the bar one, it's connecting node I and node J. So because of that, the forces coming out from the bar one will not have any effect on the third node, node K. And similarly, the bar two is connecting the node J and node K, and therefore that forces, the bar two's forces, it will not have any contribution to the reaction forces in the node I. And so we add a bunch of zeros basically to these vectors from both the bar one and bar two. We get them into these 9 by 1 shape, and then we do the vector sum, and that will give us that global force. So this is as simple as that. Um, so basically in the middle, in the jth node, it sees both of the contributions from the bars, from the first bar and also from the second bar. And depending on how you organize the node, so here in the first bar, node J is the second index, whereas in the second bar, the node J is the first index. So the sum would be bar 1 4 and bar 2 1. That will give us the force in the J's node in the x direction. So 1 also means x in this case. And similarly, for the forces in the y direction, it would be bar 1, the fifth index, that's related to the this place here, sums the bar 2 2. So just pay a little bit attention to these subscripts index because sometimes they change. But overall, it's not too crazy. And then after that, we obtain this global force, and now it's a 9 by 1 vector. Okay, great. That's what we're looking for. And the next thing I hope to do is to just compare and let's see if I indeed get the same global force if I do the same thing with the stock function. So in the stock function bar element, there's this solve global force. So this is just to set up that function, the system, and then we have x1, xj, xi, xj, xk undeformed, and then I'm gonna come up with that deformation U factor, a U matrix. So this is the deformed configuration. And I add a point 0, 1 deformation to the second node in the z direction, the third direction, right? That will lift this second node upwards a little bit. And I try to solve for the forces. If you compare these and these, they're identical, showing that what we've just done is indeed accurate. So without further delay, let's go into the stiffness matrix assembly. So this looks a little bit intimidating, but actually it's just like what we've done. So in the stiffness matrix of a system with three node, we're gonna have a stiffness matrix that is 9 by 9 because each node has the capability of moving in the XYZ direction, and there's going to be a stiffness associated with each of that moment in those directions. So, and again, so in the first 3 by 3, it is the forces you're going to be seeing when your node I moves in the corresponding direction. So the forces on node I when node I is moving in that corresponding direction. So the case, the final 3 by 3 matrix here, it would be the forces acting on the node K when the node K is moving around infinitesimally at its local place. And same thing here with the node J, this 3 by 3 in the middle. It would be, so basically here, the 3 by 3 in the middle, from the fourth index to the sixth index, that would be when your node J moves, what kind of forces the node J sees, infinitesimally. And this off-diagonal terms, these three matrix, it's connecting node I and node J. So that's basically telling us, what if my node J moves, say infinitesimally in its local coordinate, and what will happen to the forces at node I? So what kind of forces node I sees when the node J is moving, having some infinitesimal motion locally? So the bar 1, because it's connecting node I and node J, when we calculate the bar 1 stiffness matrix, it's going to be 6 by 6. We need to fill it into the first six indices in this global stiffness matrix. And for the bar 2, because it's connecting node J and node K, we're filling the remaining, the last six. So from index 4 to index 9 in the global stiffness matrix. And please pay attention here in the center part where there's overlapping, you always sum the forces up or you sum the stiffness up. If you overwrite the value there, you probably will get the wrong result when you try to link the stiffness with your nonlinear solvers. But anyway, so with the code we built in section 05, we can come up with the bar stiffness from the first bar and also the second bar relatively easy, right? Just call these functions, which we've used in section 05. We're going to get two 6 by 6 local stiffness matrix, and we just sum them and put them back in the global stiffness matrix. So the nice thing about these formulation we're currently using is that you actually don't need to do any sort of coordinates rotation. So if you're doing these with, let's say, the frame or the beam model, when we first start doing, say, matrix structure analysis class, many of the problem arises when we start need to rotate the stiffness matrix because the way those matrix were derived, they are using a specific local coordinate, and when you want to integrate that into your full structure, you always need to do some sort of a coordinate rotation to make sure that everything is aligned. But here we actually don't need to do that. That's because of the way the central difference just kind of take care of many of those things. And also, like in our node representation, we don't have rotational degrees of freedom. That actually makes our life a little bit easier here. I'll show you how we can eventually capture model through the introduction of 3-point rotational spring and also 4-point rotational springs later. But at this point, let's just still stick to the truss system we have. So with these matrix assembly, we eventually can add the two things together. So this part of the code is basically just adding these first the stiffness matrix, local stiffness matrix from the first bar to the first 6 by 6 location. That's done here. And then add the rest, add these 6 by 6 matrix from the second bar to the bottom. So this is where there's overlapping, and we're writing it with a very simple for loop. So it starts for the first element and then it keeps on going. All right, so we have the Smith matrix from these manual processes, and we want to compare that with the stock element that we derived here. Just visually inspected, they are identical. That's great, right? This is exactly what we are looking for. So this is something that is pretty cool, and it's basically just indicating that we're doing the right things. So, but of course, in reality, the structure gets more complicated. So for instance, for a truss system to be used, let's say in the civil engineering environment, we typically have much more bars or much more trusses. It's definitely going to be more than, I don't know, two trusses. So we want to automate the process of these matrix assembly. And this is what we're going to be getting into with these 6.3 subsections. So how can we do that through using a for loop? So if you're coding, you don't want to, manually add, I don't know, if I have 100 bars, I need to manually adding 100 bar stiffness matrix and sum them. That is not something we want to do, right? We want to make things automated. So that's represented using this next example. So we're gonna be dealing with a 6 node, 9 truss type of system. So we've expanded our structure up. So it's kind of forcing us to write a for loop, and I do really want to show you how that works. So the first thing we want to talk about is how do we want to actually represent such a structure. I have 6 nodes and I have 9 trusses. Right, so for the node, definitely there's going to be a nodal coordinate. It's going to be a 6 by 3 kind of a matrix. Well, each of the rows basically tells you where each of the node is located at. So for instance, node 1 would be 0, 0, 0. Node 2 moves a little bit forward in the x direction. Again, we assume that we're looking at a XOZ plane. So there's going to be an axis that's perpendicular to the screen. That's the second one, which is 0 throughout. And the third node is this one. So far, so good, right? Rather easy. And then for the deformed node would be just like the nodal coordinate, but I want to push the second node downwards in the z direction by 0.05. So that's done here. So this second node, third direction moves down by 0.05. So that gives me the deformed node, another matrix. So the next thing I want to do is to use another matrix to represent how these bars are connected. So for instance, I have a bar 1, it's connecting node 1 and 2. Because of that, I have 1, 2 here. So it's just like you defining those stock elements with saying in the calculation example. We need these structures to give us a more effective representation of the full active system we're going to be modeling. So on and so forth. The second bar is connecting 2 and 3, and we keep going. So we need to have a total of a total of 9 bars. So they're all marked here in these figures. So your 9th bar would be connecting 5 and 6. Let's see if that's the case. Right, that's indeed the case. And the next vector is basically storing the length of the bar. And we have the first 1, 2, 3 is 1. Number 4 is square root of 2. And then 5 is 1, square root of 2, 1, 1, 1. So this is what this vector is. Basically, when the bars are not deformed, what's their original length? So for this gray shaded area, without the deformation applied to the second node, that's what we have. And the node number, and then the bar number can be calculated using the size function. That's one way of finding the dimension of a vector or the dimension of a matrix in MATLAB. So we can find their number. So it will return a 2 by 1 matrix, a 2 by 1 vector with the first index indicating the length in the first dimension and the second index indicating the length of the second dimension. So the number we're looking for the first. So how many rows are used there. So that's what this means. And after that, like we've discussed, for the global force vector, it needs to be the number of node times 3, and it's going to be a vector. So zeros, node number times 3, 1. That will give us the appropriate global force vector. So here's just an automated version of doing what we've done above here, the force assembly. So this is very manual, but we want to make that process more automated. So the for loop, it's gonna loop through all the bars. So that's why it's for I from the first bar to the final bar number. And we're gonna need to find the nodal coordinate of the i's node and the jth node for each of the bar. So the node I and node j indexes are, defining this bar connection, right? So this is your ith bar. The first index gives you the first node, this one. Let's say if I is 1, 2, 3, 4, 5, this is 2. If I is 5, this node j will be 5. That's what's going on there. And then we find the nodal coordinate. We try to extract that node number and use the node number, and these will give us that entire row that will give us the final 3 by 1 vector for the nodal coordinates of the ith nodes in this case. So now that I have these two, what I can do is use that bar function we created last time to find the local force out of the system using the xi node and xj node, the length of the bar for the ith bar, and EA is 1 throughout this entire example. So after that, what I do is I will sum the first 3 index of this local force vector to those to the node I that's in the global force vector to the appropriate indexes, and the indexes are calculated as 3 times node I minus 2 to the 3 times node I for the node index. If you're doing in Python, you might need to change this a little bit because the index in Python start from 0, whereas here in MATLAB it starts from 1. I know that that little difference makes a lot of people furious, but you'll get used to it. Over time you get used to the coding. But then the same thing. So for the fourth and to the sixth, it would be the jth nodes here. So that's actually insert a random command so that I can stop here, and let us work together to see what exactly is going on here. All right. So I'm going here, and let me pull out that global force vector. So something is added to the first 3 index and the second 3 index from 1 to 6. So why is that? I've just been through the loop for I equals 1. So I just figure out the first bar. The first bar is this 1, 2 bar as defined here. It's connecting node 1 and node 2, and therefore these bars reaction forces are added to the first and the second index. So what will happen if I get it run for the second loop? So now this time the I is 2, right, within this loop. And if I go to that global force, you can see that the second index value get changes. If you are not convinced, you can, go back a little bit in the video and try to convince that for yourself. But it is changing because there is a second bar's force. It get added to these 4 to 6 index, and on top of that, so because the second bar connects bar 2 and bar 3. So what will happen is if you go back here, another force coming out from the second bar is added to these 7th to 9th indexes. So these are associated with node 3, right? So this is 18 by 1. That's node 1, node 2, node 3, node 4, node 5, and eventually node 6. So if we keep going, each time. So this time it's I equals 3. Third bar would be adding something to the 1 and 4. Is that what we have? Yeah, that's indeed. So my node 4 now sees some forces because the force bar's reaction force has been added to that global force vector. All right, so I can keep on doing these. So let's see, I've looped, I click it twice, so I'm now doing it uh, node 5 right now. And node 5, I have something added to the fifth node. That's expected. And if I keep adding, going for another loop, I would be dealing with I equals 6. So the sixth node, oops, sorry, here. So the sixth node is connecting 5 and 3, so I should not see anything related to node 6 yet. If I click next, right, I equals 6. So yes, indeed, node 6 still don't have any reaction. Um, and I need to click it again until I equals 7 because the 7th bar do connect node 3 and node 6. There we are, I equals 7. Indeed, okay, there we are. I have some very little forces there because, because nothing is really deforming that large. So this is really supposed to be very close to zero, right? Basically that seventh node are not really deforming that large. So this is exactly what this for loop is doing. It goes through each of the bars, it finds the reaction forces from all of the bars, it sums them into the appropriate location, and after um, looping through the entire number of bars, we eventually get up these global force vector. Okay, so now we have it. Let's compare that with what we have from the stock function. So we do the same thing. There's going to be 9 bars. So the A vector and the E vector are 1, are 9 by 1, 9 by 1 vector here. It's all ones. And then the node ij mat is just the bar connection we just created. And the UMAT is basically the deformed nodal coordinate minus the nodal coordinate. And at the end of the day, we find that global force vector from the stock function, and we want to compare that with what we just computed. And as you can see, our result is a zero vector, so this is exactly what we hope to see. It indicates that we've done a good job, so this is right computation. So we're happy about it. And what we hope to continue working on in this next set of a code is to actually plot out what kind of global forces we're getting for this particular small truss system. So here we're just going to be revisiting some of those plot functions we are doing in the section 05. So plot 3 is going to give you a 3D line segment, and this is the first nodal coordinate. This is the second nodal coordinate, and this is the third. So X, Y, Z. That's what they are. I have 2 nodes. I need a line segment connect 2 nodes, and that's why for the X coordinate here, there's 2 value there. And this is the Y coordinate. So if you need more information, you can go into the MATLAB's official website, and that would gives you more introduction about how to use plot 3 function, for instance. So for the same thing, I do this undeformed nodal coordinate with some gray color, and then I do the deformed coordinate with the black color. And then on top of that, I want to use these force using this quiver 3, which is also something we've used in section 5. I would like to go through all the node, find their local forces from the nodal force, basically the global force functions from I to the correlated index inside of that. And I use these quiver 3 to plot a vector, a vector that shows where the node is pointing. So after doing all of these, you actually already see the results down here, right? So this is the force I need to apply to maintain equilibrium, basically. So this bottom node is get moved downwards by 0.05. It gets very direct stretching deformation in the center bar. So in order for me to maintain equilibrium, what I need to do is really, drag these force node and also the second node and apply a pair of forces in the opposite direction to try to stretch it so that I can maintain the equilibrium. If I let go, if I do not provide these forces showing in the red arrows, this thing will snap back to its original deformation, zero deformation location. So it will snap back to that gray shape. So this matches our expectations, right? We're only moving these nodes downward. So these bars do get extended a little bit, and as a matter of fact, you can see a little bit of a red on the side. So they do get a little bit of attention force, but those are not big enough to be showed in these diagram. So this matches our expectation. We seems to be doing a good job. So let's keep moving on to make the stiffness assembly also automated. So we're gonna be doing, again, exactly the same thing. We loop through all the bars. We first create this global stiffness matrix, which is node number times 3 by node number times 3. So that's the size of it. Because we have 6 node here, so this particular matrix will be 18 by 18. And then when I create a local matrix, it would be 6 by 6, and then I need to put that 6 by 6 to the appropriate location. So this would be also fun to watch. So in action, let's add a random line so that I can stop there and start to get into the loop. So this time what I hope to look at is the global stiffness matrix. So global stiff, I can actually drag it out, right? Yeah, that would be so much better than going back and forth. I will be able to see it. And let me change my, okay, there we are. Okay, that would be so much better. So right now, IS1, we're just working on the first bar, right? So the first bar is connecting the first node and the second node. So node 1 and node 2. So node 1 is related to this part. It's a 3 by 3 matrix. Node 2 is here. And then there's always these cross diagonal terms that tells you how much forces you have in node 1 when the second node get moved. So looking good. So let's keep moving. We're now doing the second node. So you can see that this part of the matrix get changes. There's one more local stiffness matrix being added here, and that's connecting node 2, which is related to row 4, 5, 6, and column 4, 5, 6, and also row 4, 5, 6, and 7, 8, 9. So that's the second node. And then the third node would be 1 and 4, right? So you would expect something show up here. Indeed, that's what happened. So 1 and 4, 10, 11, 12 for your global stiffness matrix is related to node 4, whereas 1 to 3 is related to the node 1. So your cross diagonal terms are happening at this location here, right? So that's node 1 and node 4. And again, node 1 and node 4 in these 1, 2, 3, and 10, 11, 12 location. So I can keep going it and going in, and each time it's going to adding another bar's stiffness contribution, and gradually it's going to fill the entire matrix until eventually there's going to be something added to connect to the final load, and our I will become 9. So that's the last bar we added in, so we can monitor how this for loop is working on through stopping it in between. So I hope this helps you to get an idea of what this is doing. And then as usual, what we hope to do after creating these code is to compare what we've got with the stock function. So solvefk here for that bar class in the package. So we get this global k from the stock function, and it actually matches the global stiffness exactly. So when we take the minus here, we get a 18 by 18 zero matrix that's telling us that indeed we've got the result right. So we're going to be happy about it. All right, so I hope this gives you a overall idea of what we're talking about when we're doing these stiffness matrix assembly and also the internal force vector assembly. So if you go into the source code of the element, what you will see is that the code we just wrote, for instance, these for loops are just what's happening here in the soft global force and the soft global stiffness um, um, functions inside of that stock class stock element. So for instance, the full soft global force, right? We find the bars, the number of the bars, we find the number of the node, we create a T-bar, which is the forces of the bar, that's the global force vector, and we find the two node, we find what's their coordinate, and we solve for that local force function. And then we put this local force into the appropriate location in the global matrix, a global vector here. So this is exactly the solve global force function, how that works. And similarly, if we go to the solve for global stiffness functions, we have, the node 1, node 2, x1, x2, find the stiffness, local stiffness, it's 6 by 6, and then we put this 6 by 6 matrix into the appropriate location of that global stiffness matrix. So that's what's being done. So with the truss, with these large deformation truss elements, one of the nice thing is that we do avoid a lot of the coordinate transformation that typically might be needed if we're doing the more standard methods in, let's say, that we are learning from matrix structure analysis. So that's actually one of the nice things, makes our life a little bit easier. And the related class for this type of material, I guess if you're from civil engineering, then in one of the undergraduate class, matrix structure analysis typically will cover this related material regarding how do you put together a stiffness matrix from a single element and combine that into a full structures stiffness matrix and also the internal forces. In the mechanical engineering, most likely you probably see this first in the intro level finite element class in the undergrads, I would suppose. That could start with a 1D heat transfer, heat conduction problem, or a 1D mechanical problem, where so basically the underlying boundary value problems are the same in heat conduction and also in the equilibrium of deformable body. But then in those places, we do typically need to do some sort of these matrix assembly process to when we try to represent that 1D process into a with multiple elements. So this is usually what we would need to do. And that's typically where you are going to be able to find these material. And it's a pretty standard practice, and typically I would say that if you're going into the grad school, the expectations is that this is not too new to you, but still, I would say it would be a very good idea to actually give it some sort of review, right? Just in case people get rusted here and there. So I think the best thing to really get an idea of what's going on here is really to have a working for loop, and really you just insert something and you stop there per iterations inside of the for loop and start watching how that variables are being changed as you proceed one bar after another bar during that assembly process. So that's probably the most informative thing to learn you can do to learn and make sure that you know what's going on, even if some of the memories are getting rusted. So this is some exercises I definitely encourage you to do and make use of this code just in case you want to refresh the memory a little bit. All right, so with that, we're finishing up the section 6 on topics of the stiffness matrix assembly. And next time, what we hope to do is to move on to the section 7, excuse me, to start talking about the Newton-Raphson method. So we're gonna start really discussing the nonlinear solvers. And this is an implicit solver and how they can help us to capture the related nonlinear behaviors in many of these active structures. So thank you very much for your attention, and I look forward to meeting you again in the next episode of next section of this series. So have a great rest of your day.